Yeah, good morning, students. In A section, there are 25 students, and in B section, there are 24. Good morning. All right. Should we wait for 2 more minutes, or shall we start based on your suggestion? Should I start, or should we wait? Can you suggest? Yeah, only the students, those who are regular, are always regular, and they are in time. So, fine. Yeah. Please text something in chat box. I would like to know who are all these, those who are regular, disciplined, and they are in time. Okay. Yes, that would be helpful. Correct. Okay. All right. So we will start. Yeah. Okay. After you type something. Fine. Okay, so today's class, welcome to lecture 29. To recall you, in the previous session, we had discussed single phase AC voltage controller with R load. To bring to your notice and to remind you that we are discussing topic that is AC to AC converters, right? AC to AC converters, where the power fed to the load is AC signal. All right. So in the previous class, we had discussed about resistive load, and these were the waveforms. I hope all of you have gone through the session. So because today's session will be continuation of the same, right? So in the previous session, we discussed R load, that is resistive load, where this was a bidirectional controller. This is a AC voltage controller, which is bidirectional controller, which means that we saw there in the output that we could control the output both in positive cycle and negative cycle as well, right? So we could control the power fed both in positive cycle and negative cycle using two thyristors, T1 and T2, in this fashion, right? So our input was AC, and what we are getting at the output is also AC signal, which can be controlled. Like you can control the magnitude of the AC signal, or you can also control the average output, that average output of the AC signal, right? So we saw in the resistive load, this is how the output would look. Obviously, I assume that you have gone through the session and you understand why these breaks are, right? These breaks indicate that no device, T1 nor T2, is conducting. That is this gap there. So this is the output because of T1, and this is the output because of T2 when it was fired, right? So today's session, we will be discussing single phase full wave AC to AC converter with inductive load. Because as you can see in most of the applications, in the practical applications, all loads are inductive type. Can anyone tell me what do you mean by inductive load? When I say in practical situation, all loads are inductive type. And please note that I'm in full screen. I'll not be able to see the chat box. I would request you to unmute yourself and speak up. Inductive load means what? Can anyone tell me? All applications, like any motorized applications, if you imagine, all are inductive loads, right? Inductive load means what? It converts current into magnetic field, isn't it? So if you imagine, like say, motors, transformers, chokes, or just to be very simple, fans, vacuum cleaners, all motorized device, name them, they are all inductive loads, right? So today's discussion will be on inductive load. If the load is inductive type, then how would the output, the AC output, what we are getting, would be different from what we had discussed for resistive load, right? So please again note, I will be in full screen. I'll not be able to check the chat box, and please stop me by unmuting yourself if you have any clarification or doubt or anything you want to discuss with me. All right. So yeah, by the end of this class, you will be able to describe single phase full wave AC to AC converter with inductive load. Please note that I have used different terminologies here to make you familiar with different terms that can be used in, say, exams. Okay. Um, they may look similar, they may be confusing, but you should understand what is the topic about, and accordingly you can recall the things. This is single phase full wave. Full wave means you know that it is understood you are able to control both in positive and negative cycle, right? And we are discussing AC to AC converter. So here you can again get one more term, say AC voltage regulator or AC voltage controller, okay, or AC to AC converter. And accordingly, whether it is resistive load or inductive load. So when I say you will be able to, describe, it means that you should be able to identify the difference between resistive and inductive load. That is the meaning. You are able to describe this single phase full wave AC to AC converter means you should be able to differentiate or highlight what's the difference between resistive and inductive load. And when you say when I say describe, you should be able to clearly explain what is full wave converter, okay, how the full wave converter works, all right. And when I say you will be able to describe, again you should be able to give the explanation of the particular converter, what is mentioned here, with its working, its waveform, where waveform will depict its working, and its mathematical expressions. So all these terms will come under this describe term, okay? So describe means you should, every class when I say you will be able to describe means all those points you are supposed to be able to do that. So this is a circuit. Please bear with the type of image there. It is slightly blurred. It is similar to the previous circuit what we had, where we have two thyristors T1 and T2 connected in anti-parallel. As you can see, input is AC type, okay, and the load is inductive, okay, where you have R and L. And the working, obviously you should be familiar by this time, okay. In the positive half cycle, when this terminal is positive and this terminal is negative of the supply, you know that T1 will be forward biased, and T1 can start conducting when you give the gate signal at T1, right? So obviously there should be gate triggering circuits which is not visible here. I'm repeating every class, you should bear that in mind. Whenever you have SCRs or thyristors in the circuit, there will be gate triggering circuit, okay? But since you are concentrating more on the application of the type of the converter here, you are not showing the gate triggering circuit, but it will be there to trigger the SCRs, okay? So in the positive half cycle, T1 will be forward biased. After you give the gate pulse or the gate triggering signal to the thyristor T1, so it will start conducting. When it starts conducting means that it acts as a switch, which means it will connect this circuit. Okay, then the load will be getting the supply. So whatever you supply here, that will be visible at the load. That's the meaning. So the power devices what we use here, they act as switch to allow the supply to reach the load, right? And what is the main significance of these power devices? As Sean had asked me in the previous class, why not just say connect it? Yeah, because we want to control the power, right? We want to control how much power reaches the load, isn't it? So that's the reason we are using the power devices here. And we know already, we are already familiar how to control the power, right? So based on the time at which we turn on the thyristors, that will decide how much power will reach the load, isn't it? So that is the significance of power devices. We have already completed 3 modules. This is the last topic of module 3. So by this time, you should be familiar with what is a power device, what its significance, what are its application, why it is used, and all that. Okay. Oh, yeah, then in the negative cycle, as you know, when this terminal of the supply is positive and this terminal of the supply is negative, then T2 will be forward biased. So it is already forward biased, but it is not conducting. But after you give the gate triggering signal to the gate terminal of T2 thyristor, then it will start conducting. So when it conducts means that it acts as a switch, it connects the circuit and the supply reaches the load. Okay. So as I said, the inductive loads, you have to imagine here, inductive loads, it can be a transformer, it can be choke, it can be fans, it can be vacuum cleaner, or any application, electronic device where you see there is a load that has a coil of wire that can produce magnetic field. Okay, that is nothing but it is called a inductive load, right? So you can imagine any motorized applications there as inductive load. So let's see how would be the output. Okay. So this is our input signal with respect to omega t. Yeah, x-axis is omega t, and y-axis, this is your input to AC converter. I hope it is understandable. Okay, and these are the time instants, that is omega t. Time means pi, in pi, 2 pi, 3 pi, 4 pi. It can continue as such. And in the negative, in the second waveform, what you have here is the gate pulses, what is shown. I have not shown separately here for thyristor 1 and thyristor 2. I have shown in a single one waveform pattern as such as gate signal. So imagine this is your gate pulse that you are applying to terminal or the SCR T1, okay, of gate terminal of T1. So I call it as IG1. So they say this pulse is given at angle alpha. Okay. So after pi, when the input is going negative, okay. So when the input is negative, say you are giving a gate pulse to the gate terminal of thyristor T2. All right. So after 2 pi, you are giving gate terminal of thyristor 1. You are giving a gate. 1 minute. I don't know what's the problem with this mouse. My mouse is not working. 1 minute. Okay, so this is, sorry, I was here. So in the next positive cycle, you are giving gate pulse to your thyristor T1. Okay, so here again it will be T2 in the negative cycle. So that continues. So I've shown here for 3 half cycles here. So since our load is inductive, and you know the nature of the inductive load, in the positive cycle, when say after you give the gate signal, the thyristor is conducting now. The thyristor T1 is conducting means the circuit is closed. The circuit is closed means there is a supply reaching the load, right? So the same supply what you apply is visible at the load. So during this time, the energy is saved in the inductor, right? Energy is saved in the inductor. And according to the nature of the thyristor, we know whenever input signal crosses pi, that is when it crosses 0, so this input signal goes negative. That means thyristor T1 will be reverse biased, and it should naturally get commuted. Commuted means it should get turned off. But here, because of the inductive load, okay, you see there is some current still flowing in the circuit, which causes this output voltage to be visible even in the negative cycle. Okay, so the thyristor T1 will conduct even for negative cycle for this duration. Okay, observe here. Observe here clearly. This waveform is typically different from the previous ones, and you should be very attentive about this. All right. So because of the inductor in the load, because of the load being inductive, so it will cause the thyristor to continue to conduct even in the negative cycle for this much angle. All right. So once the current from the inductor, that is the energy that is dissipated by the inductor, reaches 0, okay, then the T1 will turn off. The T1 will turn off. All right. Now observe here in the negative cycle, as we know, this is a gate pulse, triggering pulse that we are giving to T2, that is thyristor T2, at instant pi plus alpha. This is pi plus alpha, that 2 I have erased, it is not visible. It is pi plus alpha, okay? So at instant pi plus alpha, say if you have given this gate pulse, now you know that T2 will be conducting. So when T2 is conducting, you know the input what you have applied here will be visible at the load. So this is the output voltage what you can see because of T2 conducting. And again, because of the inductive load, so the inductor which has stored energy start dissipating the energy even when T2 it is reverse biased. Okay, so T2 will continue to conduct when the input signal is going positive. So this is the duration. For this duration, this much angle, T2 will continue to conduct. Okay, so once that energy that is stored in inductor, it is reaching 0, it is dissipated, completely dissipated, then T2 will get turned off. So this will continue. Again, in the next positive cycle, when you give the gate trigger pulse to thyristor 1, T1, okay, it will conduct. So when it is conducting, you can see the positive cycle here, it is visible, and this will cause again to T1 to conduct till this stage. So this repeats. Okay, I hope I'm able to explain it and you are able to understand how this waveforms depicts the working of the single phase full wave AC to AC converter. All right. So there are different terms here that you have to pay attention to. Now this alpha is the firing angle or the delay angle, all right, and beta from 0 instance till when the thyristor is conducting. Say, for example, we'll take thyristor T1, okay? From 0 instant till when the thyristor T1 is conducting is called beta, which is called extinction angle. Okay, that means it means to say the duration at which thyristor will turn off. Okay, till then it is from 0 to at what time thyristor will get turned off is called beta, which is extinction angle. Okay, obviously from the waveform it is understood the gamma which is shown here. Okay, the output from this instant to this instant. All right, gamma, it is obviously beta minus alpha, which is called conduction angle. So these are the terminologies which you have to remember in these waveforms. I'll repeat, alpha is the firing angle, beta is extinction angle, okay, and gamma is conduction angle. Alpha, the firing angle or the delay angle at which the thyristor will start conducting, okay. Beta is the time duration at which the thyristor will stop conducting after it is turned on. All right. And gamma is the duration at which the thyristor remains conducting. So as you can see, I've shown here, this is the time duration at which T1 is conducting, that is gamma. So gamma is given by beta minus alpha. So all these are terminologies I'm repeating. You have to remember in these waveforms. Am I clear? Am I clear? Can anyone acknowledge? Are you able to understand? Okay, thank you, Sanket. So the last waveform, what you can see here is the output current. Now observe the output current here. Since inductive load, yeah, so the current will slowly increase, that is exponentially it will increase from the duration at which the thyristor is turned on. Okay, so slowly the current is increasing. So in the negative cycle, as you can see, because of this inductive current, all right, the current that is flowing in the circuit is because of the energy that is stored in the inductor. So the current is now decreasing. You can say the energy that is dissipated by the inductor. So there is the flow dissipation of the energy that is stored from the inductor, right? So current is now decreasing here from this duration, from pi to this instant. Okay, as you can see, current is decreasing. Now in this state, after thyristor T1 is turned off and till the duration, the next pulse is given to T2, it is not started conducting. So at that stage, no device is conducting, so current will be 0. I hope you are able to relate that. Okay. So again, in the negative cycle, as you can see, this is instant. It is because of the inductor. Okay, current is slowly reducing here, dropping to 0. Once it drops to 0, that is when thyristor T2 will stop conducting. Okay, then till you give the next pulse, there is no current because none of the devices are conducting, so there is no current, and this repeats. So as you can observe that the output voltage, what you can see is a variable output voltage, what you can observe here, which is a continuously varying, because in the positive cycle T1 is conducting, in the negative cycle T2 is conducting, so you are having a AC signal at the load. And if you observe the current as well, it is a continuously varying current. So there is a AC voltage and current that is reaching the inductive load, but obviously the magnitude will be varied depending on the angle, the alpha angle at which you turn on your devices, right? So imagine if you have turned on somewhere here, alpha is equal to 90 or pi, so you would have got the output from this, right? So here to here. So if you calculate the RMS voltage here, then the RMS voltage that was calculated from here compared to from here, the area, the total area, what you can see here for this or for alpha is equal to pi, that then obviously it would be different, right? So if alpha is equal to, pi by 2, then the area what you can see here will be less compared to what exactly you can see here. So obviously the RMS voltage, output voltage of the load would be different depending on the alpha angle. So same with the current as well, right? So this is the waveform that is shown in the textbook. I wanted to show you with the different timings here. Here it is slightly confusing. So I drew it and here is a comparison. So this is the input waveform. Okay, this is taken from the textbook, and observe here in the textbook, the name is single phase AC voltage controller with RL load. All right. So it can be AC voltage controller or AC to AC converter. Yeah, based on it, the terms can be different. So this is your AC supply. This is your output voltage. So this part, continuing from the next cycle here, it is shown here. So that is what is visible here. Okay. So alpha here in the textbook, it is shown somewhere near to pi by 2. So the output what you are getting here is from here, and this is the output because of the inductive load. And this is when both the devices are not conducting, and pi plus alpha is a time when the next thyristor T2 is turned on. So this is the output what you are getting, and because of the inductive load, it has continued in the positive cycle as well. And this is the duration where both the devices are turned off, and 2 pi plus alpha is when the next pulse to T1 is given. So that is when T1 will be conducting. So that is what is shown here. This is your output voltage. All right. Current. This is your output current that is shown in the textbook. Okay. So the time the thyristor is turned on, current is slowly rising. Okay. So in the negative cycle, because of this inductive energy that is dissipated, so current is slowly reducing. It is reaching 0. At this instant, the thyristor will turn off, and the duration when both the devices are not conducting, current will be 0, shown here. And when the T2 is conducting, current, as you can see, it is slowly raising. Okay. And for this part, it is reducing because of the inductive load. And for this duration, both the devices are turned off, there is no current, and this cycle repeats. So that is what is shown here. Okay. So I just wanted to avoid the confusion, so I drew this with respect to the input, output voltage, and the current. So just to avoid confusion. And obviously this last waveform, what you can see is the voltage across thyristor. You can imagine the two terminals where both the devices are connected. Okay. So this output is when the thyristor, okay. So initially, let's start here, from here. So when the device is not turned on, okay, the voltage across T1, as you can see, it is following the input. So this part of the input, when it is not turned on, okay, now you should be able to relate that. You should be able to give the understanding of the working of the powers devices. Yeah. So voltage, it is same as the input what you have applied. Once it is turned on, when the device is turned on, the voltage across it will be minimum. Okay. So that is shown here as 0 when it is conducting. So in the negative cycle, this is the output because of T2. Yeah. So when it is not turned on, the supply voltage what is applied is visible. Okay. When it is turned on, this is the duration when the thyristor is turned on. So voltage across the thyristor will be minimum for this duration. So the cycle repeats. So if anyone has doubt, any point, I will pause here. I hope everyone understood the waveforms. If anyone wants me to repeat any part, I can do that. Please let me know. The next part is mathematical expression, derivation of the RMS output voltage and current. So before that, I just want to know whether you followed or not. Are you able to relate the waveforms, working of the circuit? Yeah, when I ask question, it means that I'm expecting some answer here. Should I ask particular person? Then I would do so. Joshua Fernandez, is it clear? Have you followed? Joshua Fernandez. Okay, yeah. Lishma, have you followed the waveforms? Are you able to relate the working and waveforms? Okay. Why all of your mics are not working, is it? Okay, who is this? Ravi? Ravi from B section. Yeah. Did you understand the waveforms? Are you able to draw the waveforms? Okay, Nikhil Shetty. B section, Nikhil Shetty. Nikhil, you're not there. Very good. Okay, Sanit D'Souza. Sanit, did you understand waveforms and working of the circuit? Is there any confusion? You want me to repeat anything? Okay, fine. All right, then I'll proceed. Thank you for your reply. All right, the expression, the RMS value of the output voltage. So, look at the waveform expression there, and here I would like you to copy down all these waveform, expression, derivation there. So, starting from this stage where V naught R is nothing but the RMS value of the output voltage. Now, observe the waveforms what we had. Okay, RMS value means what? What are we taking? We are squaring the signal, taking its mean and taking the root of it, isn't it? So that is RMS value. So the signal what we are getting is nothing but the VM input signal, the AC signal, that is Vm sin omega t. Imagine that the input signal Vs, what we have applied, the AC single phase AC signal is Vm sin omega t. All right. The output what we are having, let me go back to the waveform. The output what we are having here, it is from say alpha to beta, isn't it? And if you can see, if you are squaring this part of your response, so that is what we have to do, isn't it? And even if you square this part of the response or the output voltage, so this will be something, the square will be the positive value. Can you understand what I'm saying? So if you square this area of your output, even that will be positive, isn't it? So if you observe that the response is repeating for every pi radians, isn't it? So the output, we can take it from alpha to beta, so which could be repeating every stage. So that's why we are taking the limits from alpha to beta, all right? So Vm sin omega t square, obviously with respect to d omega t. So since the squared curve is repeating at every pi radians, so we are dividing it by pi radians to take the mean, okay? And obviously under the square root. I hope you are able to understand this. So the RMS value of the output voltage, it is given by this. So just now we have to simplify. We have to apply trigonometric equation there and come to the final expression. So what do? Take 1 by pi outside, okay? Limit integration, that is between alpha to beta, squaring of this input signal, Vm square sine square omega t d omega t under square root, all right? Then taking Vm square by pi outside. So sine square omega t, you know, it is 1 minus cos 2 omega t by 2. So taking 2 outside here. Please note down the steps there. So integration of the equation, trigonometric equation of sine square omega t, that is 1 minus cos 2 omega t within the limits alpha to beta with respect to d omega t under the square root, okay? Then in the next step you have Vm square 2 pi, okay? Applying the integration there, this will be omega t minus 1 by 2 cos 2 omega t within the limits that has to be applied is alpha and beta, okay, under the square root again. So taking Vm by root 2 outside, 1 by pi, apply the limits. The higher limit is beta minus alpha minus 1 by 2 sine 2 beta upper limit minus of minus plus 1 by 2 sine 2 alpha, again under the square root. So the RMS value of the output voltage, final expression, what we are getting here is Vm by root 2, 1 by pi, Vm by root 2 within the square root, 1 by pi, beta minus alpha plus 1 by 2 sine 2 alpha minus 1 by 2 sine 2 beta. Okay, this is the final expression for RMS value of the output voltage. I will just give you some time to copy down. Please copy down. And please, someone can speak up and say when I have to continue. Can I continue? Have you completed? Yeah, in the textbook, the derivation looks slightly complicated. Please copy down. Obviously, I will be sharing it later, but when you copy down right now, it will be helpful to recall things later. So if you're done, can I proceed? Yes. Now, the expression for the output current, I naught, okay? Now, if you recall there, the current is exponentially rising and decreasing, the waveforms, if you recall. So the output voltage, according to the mathematics, will have two components. That is, it will have steady state and the transient component in the output. So the output current will have two components, steady state current and the transient component. So the steady state component of the circuit, that is RL circuit, okay, it is given by I naught steady state, which is given by Vm by Z sine omega t minus phi, okay, where Vm is the magnitude or the maximum voltage of your input signal, and Z is your impedance, right? And phi is the phase angle, where phase angle for RL circuit, it is given by tan inverse omega L by R. Please note down all these expressions as we go on. So the equation number will be, number 1 will be the output current includes both the components, the transient state component and transient component for RL circuit. The steady state component of the current for RL circuit, it is given by, we already know this, Vm by Z sine omega t minus phi, call it as equation 2. The phase angle phi, it is given as tan inverse omega L by R, call this as equation 3. Then impedance Z, it is given by under square root R square plus omega L whole square. So this equation, we'll call it as equation 4. I'll give you some time, please copy down. So the steady state component of the output current will be equal to, just substituting the R there, Z there, you will call this equation 5. So the transient component of the output current for this RL circuit, it is given by A into e to the power of minus R by L into T. Okay, so this we'll call it as equation 6. So how have we got these two components, steady state component and transient component? So if you consider there, so say one thyristor. So when thyristor 1 is conducting, it is acting as switch, right? So the circuit would look like this. This is your input Vs, which is Vm sine omega t, and this is your RL load. All right. So applying KVL to this, you can write Vm sine omega t is equal to R into I naught. I naught is your output current. Okay. I naught of t, because this circuit has both steady state and transient, which means that the property of the output will be varying with respect to time, right? So I naught with respect to t, I naught of t plus L into d I naught t by dt with respect to t, because of the inductor. Okay, this you call it as equation 7. So because of this, we have got the two components there, the steady state and the transient component. Okay, substituting from say 4 and equation 6, we have I naught t, the total current. It is given by Vm by Z sine omega t minus phi plus A into e to the power of minus R by L into T. Call this as equation 8. So this is the output current, where we have substituted both the steady state and transient component together to get the final output current. But here, as you can observe, A is the constant. So we have to find out the value of the constant A here. So call this as equation 8. I hope you are copying down. So calculation of constant A. So recall the waveform. I'll go back to waveform. Yeah. So for alpha angle, if you observe, current is 0, isn't it? So substituting that here, from the waveform, we can write I naught t is equal to 0 for omega t is equal to alpha. Call it as equation 9. So from this expression, T can be written as alpha by omega, call this as equation 10. Now substitute this I naught of T is equal to 0 in equation 8. So 0 is equal to Vm by Z sine, just in the previous equation, equation number 8, we are substituting all terms, that's all. Vm by Z sine, in terms of omega, let us substitute with alpha, alpha minus 5 plus A into e to the power of minus R by L. In place of T, we will substitute alpha by omega. Call this as equations 11. Okay. So taking this constant term to the left hand side, which we want to calculate the value of A. So A into e to the power of minus R by L omega by alpha by omega, that is the term taken here, is equal to minus Vm by Z sine alpha minus 5. Call this as equation 12. Okay. So A will be equal to the right hand side, that is minus Vm by Z sine alpha minus 5 divided by this term, e to the power of minus R alpha by omega L. So call this as 13. Okay. Now A will be equal to minus Vm by Z sine alpha minus 5, taking this denominator to the numerator, e to the power of, this will become plus R alpha by omega L. Call this as equation 14. I hope you are noting down. Okay, now substitute A. So this is the value A what we have got. Substitute that in equation 8. So that will give you the output current. Okay, I naught of T, substituting A here, what you have just calculated. I naught of T, what we had, equation 8, Vm by Z sine omega T minus 5, plus in place of A, we will write minus Vm by Z sine alpha minus 5, e to the power of R alpha by omega L into e to the power of minus R by L into T. Okay, so just removing the bracket here, Vm by Z sine omega T minus 5 minus Vm by Z sine alpha minus 5 e into R alpha omega L into e to the power of minus R by L T. So combining these two exponential terms, okay, combine these two exponential terms, we have I naught of T Vm by Z sine omega T minus 5 minus, that is taking Vm by Z outside, sine alpha minus 5 e to the power of, taking R by L common here, taking R and R by L outside, you have alpha by omega minus T. So this is equation 15, which is the final equation for output current. So as I said in textbook, the derivations are not clear. Step by step derivation is not clear there in the textbook. So I hope this was simplified and you have understood. So that is about single phase, full wave, AC to AC converter or AC voltage regulator. So we have described the circuit there. We have described its working. We have seen that AC signal that is reaching the inductive load, how it varies. So we have found out the RMS output voltage. We have derived the expression for RMS output voltage, and we have also got mathematical expression for the output current, which are both AC in nature. So that is about today's discussion. If you have any doubt, any clarification, if you want me to repeat any point, I can do that. I hope you have copied all the steps there. Any doubt at any point? Or you want me to repeat anything? Is it clear? Yeah, even I can be silent as you guys are. Okay. Um, okay. Yes. So if you have um, anything to ask, anything to discuss, you are free to do so. All right. At this point, the time is 9:52. I want everyone to enter your USN number. Don't want, thank you, madam, yes, madam. I want your USN number. 9:52. I'll note down. Enter your USN number in the chat box. Because I can see like few people already left. In B section, there are 44 and A section 48. So that completes module 3. Maybe you can expect one assessment there in a couple of days. Please, I would like to bring to your notice, please note down the terms, all they are confusing. It looks like all are same. Single phase half wave converter, single phase full wave converter. So according to whether it is AC to DC converter or AC to AC converter, what we have discussed till now, you should be able to differentiate and able to describe different circuits. Okay, so try to pay attention to that when you're studying AC to DC converter. There is single phase half wave converter, there is a single phase full wave converter, where in AC to AC converter, again you have single phase half wave and full wave. All right, so that may be slightly confusing, but when you pay attention, then it will not be. Okay, so we will end the session here. Have a nice day. Thank you. Bye. Yeah, bye, bye, bye. Thank you. Thank you. Bye.